Good morning, good evening, everyone. I'm Alicia. As you said, I was a PhD student at UNSW, and I submitted my thesis last year. I had a very wonderful time with Thais, Ruth, and Richard at UNSW, and now I'm a odor engineer at Stantec working with Ari Shaman. So today I will discuss the repeatability of flux chamber measurement for odor emission and going to ask this question, what we are really measuring. So as we all know, odor emissions are a common concern across feedlots, lagoons, chicken farms, landfills, wastewater treatment plants, and the soils. And this source release a complex mix such as hydrogen sulfide, volatile organic compounds, volatile sulfide compounds, ammonia, and methane and carbon dioxide. So over the last decades, there are a lot of methods has been developed, which are in common practice, including sampling devices, portable analyzers, and meteorological measures. But there are still some concerns which related to odor sampling methods, which the influence of sampling methods on emission is unknown. So this is part of my review paper over 150 sampling papers, and the results are showing in the few sections. So over the past decades, a range of the sampling methods has been used in scientific research and engineering practice to estimate the gas exchange at the porous media. However, there has not been a consistent nomenclature to represent the different sampling methods. For example, a variety of the terms has been used to denote an enclosed sampling chamber without consistent sweep flow.
Sorry to interrupt, Alicia. I don't think your slides are changing.
I'm in the slides which showing all the sampling methods.
No, we just see the original slide deck. Maybe if you just click on the slides that you're going through one by one rather than presenting it, I think it will go.
Cool, thank you.
Perfect.
Sorry for... So in these slides, so as I said, we have been reviewing a lot of papers, and there's not a consistent nomenclature on the sampling techniques. And for example, you have seen a name such as a closed flux chamber, or closed static chamber, or static flux chamber, or even static hood has been used to represent a same sampling devices that's without a consistent flush flow. So I understand there's no point here in arguing for correct term, but we still become clear that the inconsistent naming can be a source of confusion and misunderstanding. Therefore, this figure establishes a basis of consistent nomenclature. And you can see the sampling methods has fall into two border group, which are directly sampling methods and also hash-based methods. So direct sampling methods contain flux hood, wind tunnel, and static chamber, which are all the open bottom devices can be placed over the sample in the laboratory or in the field. Hash-based methods, which include dynamic hash-based and static hash-based, are all the methods which represent a closed container and where the sample will be put inside for sampling. I will go next slides. So according to our discussion last slides on a variety of the sampling methods, there was always a question about what led to the diversity of the sampling techniques being used. For example, if a specific sampling technique was selected because of its lower cost, popularity, or mechanistic advantage in being more suitable for using in specific sources. So to better clarify these motivations, we have reviewed 150 papers focusing on odor sampling from passive areas, from area sources, including passive and active. And of these papers, 60% of didn't provide a rationale for the choices of their sampling methods. Only 35% of the paper has given a reason, and the reason has been grouped into 3 categories, which are here. So for reason 1, we would say it's mechanistical reason. For example, like wind tunnel is a common method because it's able to simulate the wind action. And for reason 2, the paper we have concluded as a practical reasons. For example, static chamber is selected because it's simple and low running cost. Reason 3, we would like to say it's mainstream reason, specifically for flask hull, which is the most popular and widely used method because we have guideline for its operation, which is simple and easy. So clearly we can say mechanism and popularity were the 2 main significant reasons attributed to the choice of the sampling devices for capturing gases from different area sources. So even within one method, emission results vary widely with operational parameters. And there are some key influencing factors such as sweep gas flow rate and the insertion depth of the chamber, fan speed, and mixing efficiency, and also incubation conditions for the headspace methods, including dynamic headspace and static headspace. This metric figures summarize the main influencing factors for the different sampling methods and the recommendation for mitigation actions. So there are some high affecting factors, for example, for insertion depth, which is considered as a high infecting factor. So the way we to mitigate the effect of the insertion depth is trying to minimize the depth as much as possible, as long as we can ensure that good seal condition inside the chamber is well maintained. Same for the sweep flow rate. When we are doing sampling, a suitable sweep flow must be selected, not too high to dilute, and also not too low to let the gas accumulate inside the chamber. For the low affecting factors such as the presence of the fan or the fan rate, we also have related actions to mitigate the impact. So if an internal fan is not really needed, if you can say a headspace of the chamber is well mixed, but if you really want to use a fan and you need to make sure the fan speed, position, and specification must be clearly recorded and keep consistent while you are doing the sampling. Overall, the message from this table saying the method repeatability depends not only on the device type, but also on how consistent these parameters are controlled and reported. To investigate the repeatability of the flux chamber, we have set up the experiment in the lab with a control environment. So this left bottom schematic shows the setup of study VOC emission from dry porous media surface, in which a layer of the porous media is suspended above a liquid layer which acts as emission source. The non-concentration of the target VOC were added into the liquid layer. In this research, we have 2 chemicals has been selected, which are relatively stable and commonly detected from area sources. They are acetic acid and butanol. And we also selected 3 different type of solid, which depending on their porosity, organic compounds, and they are sand, cocoa coir, and soil. They are super easy to find from a local supplier. And from this experiment setup, we also have a feed chamber with adjustable sweep flow from 1 liter per minute to 5 liter per minute, and also with a mechanical mixing fan. as well as adjustable internal volume of the chamber from 20 liter to 29 liter. And here are some basic results from this from this paper. So you can see the relationship between the sweep flow rate of the flush chamber and the VOC emission rate. So generally, all the results exhibit a uniform trend where the emission rate will increase with a higher sweep flow rate. That makes sense because when you have a higher flow rate, you're gonna generate more turbulence in the surface of the dry media, which gonna improve the mass transfer of the gas. That's why it lead to a higher emission rate. Well, when you look in deeper, in the case of the porous media, the emission from the cocoa coir showed the greatest sensitivity to the sweep flow rate, while flash of acetic acid and butanol increase around 25 and 11 times respectively when the flow rate changing from 1 liter per minute to 5 liter per minute. And in the case of the target compounds, if you can see, the acetic acid represent a more significant response to the changes in the sweep flow rate instead of like a butanol across all the media. The most notable increase in emission rate was observed in acetic acid emission from cocoa coir, which in the red line here on the right figure, where the emission rate at 5 liter per minute was substantially higher than at lower flow rate. We also have done some tests regarding the relationship between the head space volume of the chamber and also the VOC emission rate. So the result has shown a general trend where the emission rate of butanol and acetic acid increase when the headspace volume decrease. And in particular, emission rate of butanol and acetic acid from sand, which are highlighted in red circle, had a sharp rise where the butanol and acetic acid increase around 100% and 70% respectively when the headspace volume was reduced only by 5 liter. So in contrast, emissions through cocoa coir and soil were not as strongly related to the variation in the headspace volume, where only limited changes was noticed for cocoa coir and soil, which means the emission rate from sand or cocoa coir might be sensitive to other factors, not only by the headspace volume. Then, follow this conclusion, we have also done the comparison between fans. And here, based on the different mechanical mixing scenario, we have namely the no fan, small fan, and big fan. As a trend, you can see the emission rate of both butanol and acetic acid has increased with the presence of fan, and the growth was more pronounced from the surface of cocoa coir, which is sit in the middle of each figure. Installing the fan can increase the emission rate. From the result, we can tell, however, the increase depending on the fan's capacity to promote adequate mixing in the headspace and create more turbulence. And this turbulence depending on the fan speed, fan size, and also the direction of the fan. Follow on this, the preliminary result we have shown here, and there are some discussion and results. So firstly, we'll say the odor measurement result highly depending on the sampling method and parameters, and which is an important factor, but many study has lack of justification and standardization. And in the experiment of the flush chamber testing, we have identified the flow rate as a dominant measurement outcome, as well as a mixing. So moving forward, there are some steps we would like to suggest you to improve odor sampling from area sources. So firstly, it will be develop standard operating protocols for chamber design and testing, and then follow with require full reporting of flow rate, chamber volume, temperature, and mixing when you are doing sampling. Thirdly, it will be a good idea to establish calibration procedure using non-emission sources and encourage inter-laboratory comparison studies to quantify methods uncertainties and get a more accurate result. That's all my presentation today. Thanks for having me, and I would love to take any question.